3.75 times 10 to the negative 7th meters. That was the first step. Then we use our C equation. C equals lambda times nu. We want to solve for the frequency, so C over lambda equals the nu. C is a constant. We look up the constant in our paper, 3.0 times 10 to the 8th meters per second. And the lambda is 4.75 times 10 to the negative 7th meters. We plug this into our calculator, 3EE8 divided by 4.75 EE negative 7. And this gives us a frequency value of 6.3158, and that is 1 over second. That's the frequency. Then the second equation we use is energy equals Planck's constant times frequency. Planck's constant is 6.62 times 10 to the negative 34th. Again, we look that up, and then we multiply by 6.31, times 10 to the 14th should be up here, pardon me. 6.157 times 10 to the 14th seconds, and it's inverse seconds. When we multiply these two together, there's a couple ways you can do it. You can plug it into your calculator, or you take this number multiplied by this number, and then you add the exponents. Okay? So when you come up with your answer, it's 6.62 EE negative 34 times 6.3157 EE 14. And this should give us a calculated value of energy of 4.18 times 10 to the negative 19 joules. The seconds cancel out, and that's where we get our energy for 475 nanometers worth of light. So those are the steps that we go through to solve a problem like this. The next question is, does the light have more or less energy than red light? What could we conclude? More or less energy? I don't remember what the red light was. Look up on your paper a little bit. Okay. The red light was 3.05 times 10 to the negative 19 joules. 3.05. This one is 4.18. So it has more energy than the red light. So if you had to make a guess as to what color this could be, what would be one guess? Could be green. What else could it be? Okay. Could be blue. Could be green. Okay. But it's probably not going to be red. Could be a brown. Maybe. Probably be one of the brown is usually a mixture of multiple pigments. So brown isn't found in the rainbow usually. But it could be a very in this case, it is more energy, so it would be near the bluer side of the spectrum. How much? We would have to, again, look more into this information. This happens to be a wavelength of blue light that has this energy. So this is how we can calculate some information about light. Since we know all about light, we know all about electrons, we're going to talk briefly about something called valence and core electrons. So, valence and core electrons. If you look up here at this picture, this is a picture of our created table we organized at the beginning of the year. Okay, what do you notice about the number of spokes on the circles?
They're consistent with each other. They're all the same.
Okay. They're all the same in what?
Each group.
In each group. What happens as you go from left to right?
There's more.
More spokes. Okay, now, you guys all saw this pattern when you created your periodic table. And everybody asked me, what are the spoke things? I want to know what the spoke things are. What are the spoke things? Tell me what they are. Relate to what? Reactivity. Maybe. We're going to check that out next. So the arrangement of electrons in their shells is highly predictable. The numbers of core electrons also exhibit patterns across each row in the periodic table. Most of the time they stay the same, except when you got transition metals and other things in the way. So if you look here at element number 34, element number 34, I'd like you to answer these questions using your periodic table for element 34. You have only 1 minute and 32 seconds to answer these. Do the best you can. Try to get to F if you can. On your mark, get set, use a periodic table, and go.
Geranium. Sorry, geranium. GA. What? There we go. Okay. So element's name and symbol is Fe. Selenium. Total number of electrons in the atom of this element is 34, right? Valence, what group is it in? It has 6 valence. Yeah. 4 electrons, and 34 minus 6, we put it 28 core. 28 core. Group number would be 6. Other elements the same number of valence would be oxygen, silicon, yeah,
All right, time is up. Take a look and see how your answers compare. Any clarifications on these here? These here. Only one that involved major math was this one here. I took 34 minus 6 to get that. And then these here, you could have written out the names or the symbols for those right here. Now, the last thing we're going to look at, or start to look at today, is something really cool that happens. We know valence electrons are involved with reactivity, but today we're going to look at how they're involved. If you look up here at this picture, lithium here is shown losing an electron, and fluorine is shown gaining an electron. Lithium right now has 3 protons. If it loses 1 electron, how many electrons does it have? 2. It's got 3 positive and 2 negative. If you add 3 positive and 2 negative, you get what? 1. Positive 1. Lithium would now have a positive charge if it loses an electron. Positive if it loses? Yes. Fluorine gains an electron from lithium. It now has 10 electrons and 9 protons. What's the charge going to be on the fluorine atom? Negative how many? 1. It gained 1 electron. Okay. What element has 2 electrons total on the periodic table? Helium. What element has 10 electrons total? Neon. Helium and neon are both what type of gases? Noble gases. And noble gases do not what with other elements? React. Because of this, elements lose or gain electrons to become like a noble gas. Now, is this a noble gas though? No, because it's got 3 protons. If it's got 3 protons, it has to be what? Lithium. It can't be anything else in the whole wide world ever. Ever! Even if I take all its electrons away and give them away. It's got to be lithium. Now, what we are going to look at is what's called an equation for an ion. This is really easy based on what we just showed. If you've got lithium and it loses an electron, you have to put the loss of electron on the right side. There are no negative signs in chemical equations. No negative signs. So lithium loses an electron, it becomes lithium plus 1, that's its charge. 0 is the charge here, negative 1 and positive 1. If I do the math, plus 1 minus 1 equals 0. If I look at fluorine, fluorine gains an electron. So we add an electron to fluorine, and it gives us the fluoride ion, which we brush our teeth with. 0 plus negative 1 does equal negative 1. Your task tonight is each of you will be given a specific atomic number. What you're going to do is you're going to make a Bohr model for this and determine what it would lose or gain to become like a noble gas what its equation would be, and then what it becomes would be fluoride ion or lithium ion would be examples of what it becomes. Okay? So I've got some harder ones up here. If you need to leave earlier, you can take a harder one. I will bring out the easier ones in just a second. I got to grab them from the back. Pick one and only one, any one you want. Ready, set, go. All right, I need someone that wants a challenging one. All right, challenging one is right here. 86. Easy one. 86.
But no, I don't. Xenon is the last noble gas, right? So I have one that should be noble gas. It isn't. I need to check what I got at.
Extra one. Tremaine didn't get one? I thought I counted them out just right. All right.
Yeah, I didn't get one.
Thought I had 42 in here. I apologize. Grab. Needs one? One? Need another one? All right.
Thank you.
Yep.
Where do we turn stuff?
I was supposed to plug those in the gauge. Yeah, I saw it. You're welcome. Thanks for reminding me. So you got song number 14.